Hello.
Good evening, sir.
Yeah, good evening. We'll start with parabola. Then once we're done with this, we'll go to ellipse and hyperbola. Okay.
Yeah.
So a little bit of theory. First of all, definition. Definition of a parabola is locus of a point which moves such that its distance from a fixed point is equal to distance from a fixed line, right?
Yeah.
Is equal to distance from a fixed line. The fixed point is called a focus and the fixed line is called the directrix. So this is your focus, this is your directrix. So when you do that locus, you will have say P, H, comma K, and let's say your focus was some point P, comma Q. This is given to you, and the directrix was some line Lx plus My plus N is equal to 0. So these two things are given to you, and you are finding the locus of a point that moves such that, right?
Yeah.
So you can use x and y instead of h comma k, and you will get the equation x minus p whole square plus y minus q whole square root over is equal to, so we'll square it, and that will be equal to lx plus my plus n whole square by l square plus m square, right?
Yeah.
So right now this is looking at like a complicated equation. What you can do is you can bring all the terms to one side and express it as an equation in two variables x and y, which looks like this: by square plus 2gx plus 2fy plus c is equal to 0. Basically, when you bring all the terms to this side, there will be x square terms, there will be y square terms. From here also x square, y square terms. And xy term will be there from these two, right?
Yeah.
And some linear terms will also be there. So eventually it will look like this, which is a 2-degree equation in x and y. And what is the condition that this equation represents a parabola? This represents a parabola. So you might have seen that condition before. The condition is h square is equal to ab, right?
Yeah.
So how does that condition come? So we can think about it from here. Since this denotes a parabola, try to think of what are the coefficients of x square and y square and xy that are going to result when we simplify this, right? So if you bring L square plus M square on this side, you will get one term like this: L square plus M square x square, right?
Yeah.
One term L square plus M square y square. And on this side, you get L square x square, M square y square. So when you bring them here, there will be minus L square x square minus M square y square, right?
Yeah.
And there will be minus 2lmxy also, right?
Yeah.
Other terms we don't care about. So simplifying these, what you get is, here you get an m square x square, L square y square, and minus 2lmxy. So you can see that A is m square, B is L square, and H is Lm, right? Minus
Yeah.
Lm. So H square will be equal to AB, right?
Yeah.
So basically what we have figured out is that in the general 2-degree equation, which looks like this, the condition that this equation is a parabola is h square minus ab is equal to 0 for parabola. And in a earlier chapter, you would have seen that this equation could be a pair of straight lines also, right?
Yeah.
Pair of straight lines condition was your del is equal to 0, and del was the determinant AHG HBF GFC, right?
Yeah.
So For it to be a parabola, you have two conditions actually. You should say del is not equal to 0 so that it doesn't become a straight line, pair of straight lines. And then h square minus ab should be 0, right?
Yeah.
Okay. Okay. So what happens if we have a, right now what we have derived is the general equation of a parabola when your focus was the point PQ and the directrix was the line Lx plus My plus n is equal to 0. That gives us a complicated 2-degree equation in x and y. So what happens if we choose some easier points and easier lines for our focus and directrix? So for example, if I choose the point a comma 0 as my focus and x plus a is equal to 0 as my directrix, right?
Yeah.
In that case, the equation will be much simpler. You will say x minus a whole square plus y square is equal to distance of x comma y from this line will be x plus a by 1, right?
Yeah.
Whole square, correct?
Yeah.
So then you will get the equation y square is equal to 4ax from there. So that looks like your standard equation of a parabola, the simplest form of a parabola equation, right?
Yeah.
So you are not getting the full 2-degree equation in x and y because you have chosen the points and the line appropriately. So the focus and directrix are like this, and the equation of the parabola becomes this. So in this case, the graph of the parabola will look like this. Y square is equal to 4ax. And here we can mark out our focus. Focus is a comma 0. Directrix is x is equal to minus a. This point is called the vertex, which is 0, 0. This line is called tangent at the vertex. This line is called the axis, which is basically y is equal to 0, right? And the parabola is symmetric about the axis, right?
Yeah.
A line perpendicular to the axis and passing through the focus is called the latus rectum, and this is the latus rectum line. And that line equation is x is equal to a, and it meets the parabola up at a comma 2a and down here at a comma minus 2a. The overall length of this is 4a, which is called length of the latus rectum, right?
Yeah.
Of this length, LR length basically denotes how wide your parabola is. You can draw parabolas which are very wide or which are very narrow. It depends on your length of latus rectum, right?
Yeah.
So you can say that two parabolas are similar if they have the same length of latus rectum. So they will look like the same type of shape, right?
Yeah.
Okay. Now, so far what we have said is definition of a parabola was when a point P was equidistant from S, which is focus, is equal to PM, which is perpendicular to the line to the directrix, or distance to the directrix of P. So in general, conic sections are defined like this: PS is equal to EPM, and E is the ratio of your PS and PM. And in case of a parabola, E is equal to 1, that is a parabola. Later, when we do hyperbola and ellipse, we'll get E less than 1 for an ellipse and E greater than 1 for a hyperbola, right?
Yeah.
And the equations are going to be derived in the same way. You just write, there will be a E here, and you'll just do this and get the general equation of ellipse and hyperbola also, right?
Yeah.
Okay. Then some basic terms and definitions. We have already seen latus rectum and all. We can say if the standard parabola is y square is equal to 4ax, what is focal distance of a point? Focal distance of a point on the parabola. Point on the parabola. So basically what we are asking is, if the parabola looks like this, if you take any random point on the parabola, what is the focal distance or distance from the focus, right? So we are trying to find out this, right? So if this point is x comma y, This is PS, right? So
Yeah.
know that PS should be equal to PM by the definition of the parabola, right?
Yeah.
This distance must be equal to this distance, which is perpendicular to the line x is equal to minus a, right?
Yeah.
So notice that if your coordinate is x comma y here, and this point is at x is equal to minus a, this distance has to be a plus x, right?
Yeah.
So focal distance of a point on a parabola, let's say the point is x comma y, is always a plus x. If the parabola is y square is equal to 4ax, right?
Yeah.
In general, we'll see later in ellipse and hyperbola that focal distance is always written as a plus ex, and e can be one for a parabola, then it becomes this formula.
Yeah.
Like for an ellipse, focal, there are two foci. One focal distance will be a plus ex, the other focal distance would be a minus ex. And then you get the sum of the PS1 plus PS2 becomes 2a, right?
Yeah.
And that same formula becomes this because E is equal to 1 for a parabola and you have only one focus in a parabola, right?
Yeah.
In a hyperbola, you will get PS1 is equal to EX minus plus minus A and EX plus A. So when you subtract, you will get 2A, right?
Yeah.
And E for a hyperbola will be greater than 1. Here, for an ellipse, E is less than 1. For a parabola, E is equal to 1. So this concept of focal distance of a point, right now we are only referring to the parabola, but in general, you can find out for an ellipse and a hyperbola also, right?
Yeah.
Okay, then let's see. Position of a point relative to a parabola. Position of a point relative to a parabola. So by that we mean, is it inside or outside a parabola? Is a random point going to be inside the parabola curve or outside? So if we draw the curve like this, we want to be able to figure out whether a given point P, H, comma K is inside or outside, right?
Yeah.
So x1, y1, let's say P x1, comma y1 is the point that you want to decide. It is outside, on, or inside y square is equal to 4ax parabola if this is y1 square minus 4ax1 is greater than 0, equal to 0, or less than 0. So if y1 square minus 4ax1 is greater than 0, it is outside. If it is equal to 0, it is on the parabola. And if it is less than 0, it is inside the parabola. You can verify that for common points. So let's take focus a comma 0, right? The parabola equation is y square is equal to 4ax. So if you put a comma 0 in this equation, you will get 0 minus 4a square, right?
Yeah.
So you see that it is negative because focus is lying inside the parabola.
Yeah.
And you can take other points and you can show that if it is positive, it is outside. The next thing we want to understand is line and a parabola, how they interact. Line and a parabola. So if you have a line y is equal to mx plus c and a parabola y square is equal to 4ax, right? Then when can we say that the line cuts the parabola like this, or touches the parabola, or doesn't intersect, right?
Yeah.
These are the three cases possible, right?
Yeah.
So in order to do this, what we will do is we'll solve the line equation with the parabola equation. Basically, put y is equal to mx plus c in this. By the method of solving or substituting one equation in the other, what you are really trying to find is point of intersection, right?
Yeah.
So if you try to solve this, you'll get mx plus c whole square is equal to 4ax, and that will be m square x square plus 2am, 2, no, not 2am, 2mc minus 4a into x plus c square is equal to 0, right?
Yeah.
This quadratic equation is a quadratic in x, and every root of this is a point that is at the intersection of the line and the curve, right?
Yeah.
So if it has discriminant greater than 0, it should have two roots or two intersections, which is this case. And if discriminant is equal to 0, it will have one point of contact, which is double roots or equal roots, which is this case, right? And
Yeah.
if d is less than 0, there are no points of intersection, right?
Yeah.
So if you apply now the discriminant, you will say that 2mc 2mc minus 4a whole square minus 4m square c square should be equal to 0 for tangent, and you will get here 16a square minus 16amc is equal to 0. So that means a is equal to mc, or c is equal to a by m, right?
Yeah.
So for a tangent condition, we get c is equal to a by m. So we know line y is equal to mx plus a by m will be the tangent to this parabola, right?
Yeah.
And the other cases are obvious, like you just say that a minus mc should be greater than 0, or that means a is greater than mc, or c is less than a by m. C is less than a by m for two intersections, and c is greater than a by m for no intersections, right?
Yeah.
The main condition here is we have understood how to find the condition for tangency, right?
Yeah.
So if suppose you know that it is cutting two places, the roots will be x1 and x2 here. And you can say from this quadratic, the sum of the roots and product of the roots are already known.
Yeah.
1 plus x2 should be 4a minus 2mc by m square, and x1, x2 should be c square by m square, right?
Yeah.
If the value or some data is given, values of c, m, a and stuff, then you will know the values here, and you will be able to find intersection x1 and x2, right?
Yeah.
Okay, then so far what we have seen is tangent to a parabola in the case where y is equal to mx plus c. We got y is equal to mx plus a by m for parabola y square is equal to 4ax, right?
Yeah.
This is called the slope form, or slope is given. Like if the slope of the tangent line is given, then you should use this, right? Because m is known here, right?
Yeah.
Obviously, not always will you be said that, okay, find the tangent with a given slope. Like if someone says find the tangent to this parabola with slope m is equal to half, then I should use this result because one variable is known. You just say mx plus a by m will be tangent, right?
Yeah.
But if someone says find the tangent to a parabola at a particular point, let's say x1 comma y1, then we don't know the slope of this tangent, right?
Yeah.
We want the equation of tangent at a particular point. So then we need to find slope of the tangent to the parabola at x1, y1. And the easiest way of doing slope is just differentiate the curve, right?
Yeah.
2y dy by dx is equal to 2a 4a, and dy by dx will come out to be 2a by y. So at this point, slope is 2a by y1, right?
Yeah.
And then write the equation of the tangent by point slope form. Y minus y1 is equal to 2a by y1 into x minus x1, right? So you
Yeah.
get y1 minus y1 square is equal to 2ax minus 2ax1. So this becomes y1 is equal to 2ax plus y1 square minus 2ax1, right?
Yeah.
And since x1, y1 lies on the parabola, you have y1 square is equal to 4ax1 anyway, right?
Yeah.
So this becomes 2ax1. So you get y1 is equal to 2ax plus x1 is the equation of the tangent at a particular point x1, y1, right?
Yeah.
So now two types of tangent equations you know. One is y is equal to mx plus a by m, which is when slope is given. One is y1 is equal to 2ax plus x1 when the point is given, right?
Yeah.
For the parabola, y square is equal to 4ax. In general, you should know that any 2-degree curve, 2hxy plus by square plus 2gx plus 2fy plus c is equal to 0. If you have any 2-degree curve, finding the tangent to the curve at a point x1, y1, there is a very simple trick to find that. Like obviously the method is to differentiate and find dy by dx at that point, right?
Yeah.
The long, it will be slightly long because you have to get dy by dx and then put it in the line equation. So the real method is the calculus method to find tangent, but there is a nice trick in coordinate geometry for any 2-degree curve, whether it is circle, parabola, ellipse, hyperbola. If you want to find tangent at a point x1, y1, what you have to do is replace x square with xx1, y square with y1, 2x with x plus x1, 2y with y plus y1, 2xy with x1y plus xy1, and keep the constant unchanged. Okay.
Yeah.
Did you know this already before?
No.
Okay, so you need to know this. This is very useful because now see, if you have a parabola like this, right?
Yeah.
I have derived this by the calculus method. Now, what can I do for tangent at x1, y1? I'll just replace y square with y1. And here there is a 2x, right? So 2a is there and then 2x is there instead of that x plus x1, right?
Yeah.
It's the same equation. You can check this for any circle or any curve. Like in general, any curve, the tangent here would be a x1 plus h into x1y plus xy1 plus byy1 plus gx plus x1 plus fy plus y1 plus c is equal to 0. This is your equation of the tangent at a point x1, y1 in general to this curve. Okay.
Yeah.
Just make a note of this. This is important to know because all the time you don't want to write the equation or try to find the equation. If the point is given, directly you can put the point in the curve by this rule and you'll get the tangent immediately.
Yeah.
We can prove this for simple cases like hyperbola, ellipse also, but you can prove this yourself. Like take an ellipse equation. For example, ellipse equation was this, right? Now, according to this rule, what should be the tangent at x1, y1 to the ellipse? There is only x square and y square. So it will be x1 by a square plus y1 by b square is equal to 1. Correct?
Yeah.
According to this rule, but you can confirm that now by calculus. You do 3-4 steps, find the slope, write the equation. You will realize that it will come as this.
Yeah.
Okay, so that will save you a lot of time. The next thing is parametric representation. Parametric representation of a point on a parabola. A point on a parabola. So let's say my parabola was y square is equal to 4ax. Now what I can say is that if x is equal to at square and y is equal to 2at, that will always satisfy this equation, right?
Yeah.
Here, t is an arbitrary parameter or a new variable that you have introduced. Arbitrary variable. And the point t on this parabola can be written as at square comma 2at, right?
Yeah.
What is the advantage of this? The advantage of this is that in general, if there was no parametric form, you would have written it like this, right?
Yeah.
But then there are two variables here, no?
Yeah.
But here is only one variable, right? One variable only t, correct?
Yeah.
So if the values of t keep changing, you can actually get all the points on the parabola. So t values can take any value. If t is equal to 1, a point on the parabola would be p a comma 2a, which is the end point of the latest rectum. If t is equal to -1, a point would be a minus 2a, right?
Yeah.
T is equal to half, it will be a by 4a, right?
Yeah.
You will realize that all of these points lie on the parabola, right?
Yeah.
Now, several things that we will do with this parametric form. So if you have a parametric form of a parabola, now what we want to do here is, if this point is, let's say, a t1 square comma 2a t1, and this point is another point q, which is a t2 square comma 2a t2, right?
Yeah.
Here t1 and t2 are two different parameter values, right?
Yeah.
So equation of chord joining them, equation of chord joining PQ would be simply y minus 281 is equal to 282 minus 281 by 8t2 square minus 8t1 square into x minus 8t1 square, right?
Yeah.
You can cancel a here, and t2 minus t1 also can be cancelled. So you'll get y minus 2a t1 is equal to 2 by t1 plus t2 x minus a t1 square, right?
Yeah.
So this is equation of the chord joining PQ, right?
Yeah.
Now equation of tangent at point P, equation of tangent at a point P. We saw earlier that we wrote tangent equation as y1 is equal to 2ax plus x1, right?
Yeah.
So now notice that P is this. It will be nicer if you simplify using the parametric form. Y1 is 2a t1 is equal to 2a x plus a t1 square, right?
Yeah.
So 2a gets cancelled and you get the equation t1y is equal to x plus a t1 square, right?
Yeah.
In general, this is a form that you need to remember. Tangent at the point at squared comma 2at to the parabola is equal to ty is equal to x plus at squared, right?
Yeah.
Suppose the question is finding normal to the point at square comma 2at for the parabola, right? If I have to find the normal at this point, right? So
Mm.
see, slope of tangent is what? Slope of tangent here is equal to 1 by t, right?
Yeah.
So slope of normal would be minus t, because normal is tangent to perpendicular to the tangent.
Yeah.
And it is also passing through this point. Therefore, equation of normal should be y minus 2at is equal to minus t x minus at square, right?
Yeah.
So that looks like y minus 2at is equal to minus tx plus atq, and that can be written as tx plus y is equal to 2at plus atq, right?
Yeah.
This is your equation of normal. Again, this is a result that you should remember. Saves a lot of time in the exam. Equation of tangent in parametric form, equation of normal in parametric form, right?
Yeah.
Okay. Then you also have an equation of, we also have an equation of tangent in slope form, right? Y is equal to mx plus a by m, right?
Yeah.
Okay. So what you need to know is that this line intersects the parabola at a particular point. The point is a by m squared to a by m. Like, see, the tangent curve was like this. The slope form equation did not talk about the point, right?
Yeah.
Slope form equation was only telling you, okay, y is equal to mx plus a by m is tangent to that, right?
Yeah.
But we don't know what the point of contact is, right?
Yeah.
So this point of contact is actually a by m square and 2a by m. How do we know that? Let's try to find the equation of tangent at this point to the parabola. And this time use a different form. Use the form y1 is equal to 2ax plus x1, right?
Yeah.
If this is a point on the parabola, which you can easily confirm by checking y square is equal to 4ax, which will come. Because y square will be 4a square by m square, and 4a into this is 4a square by m square, right?
Yeah.
So this is indeed a point on the parabola. And now if you try to put it in this, you will get y into 2a by m is equal to 2a into x plus a by m square. So 2a cancels, you get y is equal to mx plus a by m, right?
Yeah.
So the tangent at this point is definitely this line, right?
Yeah.
So now we know if your y is equal to mx plus a by m is the tangent, it is tangent at a by m square comma 2a by m, right?
Yeah.
Okay. Similarly, slope of normal, like if we want to find an equation of normal in the form y is equal to mx plus c, we already have an equation for of normal which looks like this: tx plus y is equal to 2at plus at cubed, right?
Yeah.
This was normal at what point? At square comma 2at, right?
Yeah.
Now, what was the slope of this normal? Slope of this normal. Slope of this normal was equal to, if you see, it was minus t, right?
Yeah.
Right.
Yeah.
So m for this normal should be minus t, right?
Yeah.
So if I want to write this equation, I can write it as y is equal to minus tx plus 2at plus at cubed, right?
Yeah.
At what point? At at square comma 2at, right?
Yeah.
But I can now transform this equation and say that, okay, here slope is m, which is minus t. So I can write t is equal to minus m everywhere in this and say it is mx minus 2am minus am cube, right?
Yeah.
At what point? Am square and minus 2am, right?
Yeah.
So you understand this equation is equation of normal with a given slope, right?
Yeah.
If someone said find the equation of a normal with slope 1 by 3, I will use this equation. If someone said find the equation of normal at some point, I will use this equation because the point is given, right?
Yeah.
If the point is given, then t will be known, right?
Yeah.
And then I can use this equation to get the normal. So the reason for these multiple forms, even though they are the same thing, is just that it will be convenient if you know the forms to directly use it in the question. Like it will be very fast, right?
Yeah.
Couple of more things that you need to know. Like suppose you have one tangent to a parabola tx t ty is equal to x plus at square t1y, and another tangent to a parabola t2y is equal to x plus at2 square, right?
Yeah.
Now you could have the two tangents intersecting at a point, right?
Yeah.
So what is the point of intersection of the tangents? That is what we want to figure out. So obviously you just have to solve these equations. So if you subtract, you will get t1 minus t2y is equal to a t1 square minus t2 square, which will be y is equal to a t1 plus t2, right?
Yeah.
And if you put that in this equation, you will get x is equal to a t1 t2, right?
Yeah.
You can check that. So point of intersection of not tangents at a t1 square comma 2at1 and a t2 square comma 2at2 comes out to be a t1 t2 comma a t1 plus t2. Okay.
Yeah.
This is obtained by just solving the tangent equations. But again, it is important to just remember this because there are many instances where you get situations where find the point of intersection of the tangent. So it is better to remember this. At point this, at point this, what is the intersection of the tangents? It is a t1 t2 into a t1 plus t2, right?
Yeah.
Same thing for normals. Like you can draw a normal at this point. You can draw a normal at this point and draw a normal at this point, and they could also intersect, right?
Yeah.
Equation of normals would be y plus tx is equal to 2at plus at cube, t1x, t1x, t1, and y plus t2x is equal to 2at2 plus at2 cube, right?
Yeah.
Again, you can solve this and find the point of intersection, and the point of intersection is this. You should write this down. It is a t1 square plus t2 square plus t1 t2 plus 2 comma minus a t1 t2 t1 plus t2. Again, it will be annoying to try to solve this in an exam. Okay, point of intersection of two normals, right?
Yeah.
You can solve it once to convince yourself that it is true, but eventually you have to remember this. Point of intersection of two tangents and point of intersection of two normals on a parabola, right?
Yeah.
This is intersection of tangents, this is intersection of normals. Okay, because
Yeah.
you won't have time to do it in the exam. So just remember that. Some other things that you need to know, if you have written them down, right?
Yeah, I have.
Okay, then let's say we have a chord of a parabola that passes through the focus, right? This is a chord of a parabola, right? It
Yeah.
passes through the focus. Let's say P was the point at1 square comma 2at1, and Q was the point at2 square comma 2at2, right?
Yeah.
Now, this type of chord is called a focal chord because it passes through the focus. Now we can find a relationship between T1 and T2 because we know that it passes through the focus. So earlier we saw that the equation of this chord was what? Y minus 2a T1 is equal to 2 by T1 plus T2 x minus a T1 square, right?
Yeah.
We had derived this earlier, simple straight line 2-point form, right?
Yeah.
Now you say that it passes through a comma 0. So put a comma 0 in this. So you'll get minus 2a T1 is equal to 2 by T1 plus T2 a 1 minus T1 square, right?
Yeah.
2a cancels and you get minus T1 into T1 plus T2 is equal to 1 minus T1 square. And that becomes minus T1 square gets cancelled. And you get minus T1 T2 is equal to 1, or T1 T2 is equal to minus 1, right?
Yeah.
So whenever a chord is going to pass through the focus, whenever it is a focal chord, the endpoints will always satisfy T1, T2 is equal to minus 1, right?
Yeah.
That is very useful because now if a question is asking, say, a focal chord of a parabola passes through one particular point, right? And that point is given. If you know a T1 square comma 2a T1, then you know T1 value, right?
Yeah.
So if you know T1 value, you can say T2 will be minus 1 by T1, right?
Yeah.
If it is a focal chord. So the other point also you can immediately find. It will be a T2 square. So a by T1 square and minus 2a by T1, right?
Yeah.
So given one point and the knowledge that it is a focal chord, you can know the other point directly by using this. You don't have to make a line and then solve it with the parabola and get the other point, right?
Yeah.
So again, this is a fact that is important. Then next thing is, suppose if the normal at point T1 on a parabola intersects the parabola again at another point, intersects the parabola again at, let's say, point P, which is T2, right? Then can you find a relationship between T2 and T1, right?
Yeah.
Basically the question is this, like you have one point here q, which is a t1 square comma 2a t1. You draw a normal to q and it cuts the parabola again at some point p, right?
Yeah.
We want to find out the point p. So we have the equation of the normal. Equation of normal would be t1x plus y is equal to 2a t1 plus a t1 cube, right?
Yeah.
And this must cut the parabola y square is equal to 4ax at some other point, right?
Yeah.
So it cuts the parabola at, let's say, at2 square comma 2at2, right?
Yeah.
This point p. So at2 square comma 2at2 lies on the line, right?
Yeah.
So if you put that there, you'll get t1 at2 square plus 2at2 is equal to 2at1 plus at1 cube. So this is a t1 t2 square. A cancels everywhere, and you are getting t1 t2 square plus 2t2 is equal to 2t1 plus t1 cube, right?
Yeah.
Now bring this to this side and this to this side, right? You get 2t2 minus t1 is equal to t1 common t1 square minus t2 square, right?
Yeah.
And since t2 and t1 are not equal, so this can be cancelled off and you get minus t1 into t1 plus t2, right?
Yeah.
So you get this, which is basically minus t1 square minus t1 t2 is equal to 2. So t1 square plus t1 t2 is equal to minus 2, right?
Yeah.
Plus 2 is equal to 0, right?
Yeah.
Correct.
Yeah.
And now you can say t1 should be equal to solving this quadratic, or actually, yeah, actually we don't need to solve the quadratic also. Just take t1 t2 on the other side. You have t1 square plus 2 is equal to minus t1 t2, right?
Yeah.
And then divide by t1. So t1 square plus 2 is equal to minus t1 t2, and therefore t2 is equal to minus t1 minus 2 by t1, right?
Yeah.
This is the relation. So we have derived the relation right now, but again, this is a fact that you should remember, because this will tell you that if I know a point on a parabola from which normal has been drawn, right? If
Yeah.
that point is T1, the point where the normal cuts the parabola again has to be T2 is equal to minus T1 minus 2 by T1, right?
Yeah.
Correct.
Yeah.
You know that T2 is equal to minus T1 minus 2 by T1 point, then you can find that point, right? A T2 square comma 2 A T2.
Yeah.
Okay. Then most of the major things we have seen. Some more stuff is there. One thing that is important is if two tangents to a parabola are perpendicular to each other, right?
Yeah.
Then their point of intersection lies on the directrix. Lies on the directrix. How and what do we mean? We mean like this figure. So let's say we have a parabola like this. We have one tangent like this, right? And
Yeah.
another tangent you can draw from here, which is perpendicular. Like the angle between these two is 90, right?
Yeah.
So let's say this is tangent at point T1, this is tangent at point T2, right? We have to show that this point of intersection is on the directrix, right?
Yeah.
We know that the tangents are perpendicular to each other. So equation of this tangent was what? T1y is equal to x plus a t1 square, right?
Yeah.
And equation of second one was T2y is equal to x plus a T2 square, right?
Yeah.
Then from these two equations, you know that the slope of first tangent is plus 1 by T1. Slope of second tangent is minus 1 by T2, right? Plus 1 by T2, right? Slope of the tangent is 1
Yeah.
by T1 and 1 by T2, right?
Yeah.
So since the tangents are perpendicular, we know 1 by T1 into 1 by T2 is equal to minus 1, right?
Yeah.
We know T1, T2 must be equal to minus 1. And now remember, we know point of intersection of two tangents was supposed to be what? A T1, T2 into A T1 plus T2, right?
Yeah.
Now, if T1, T2 is minus 1, this point becomes what? Minus A comma A T1 plus T2, right?
Yeah.
Directrix equation was x is equal to minus A, right?
Yeah.
So this point is definitely lying on the directrix somewhere, right?
Yeah.
So what this means is that from any point on the directrix, you can always find two tangents to the parabola that are perpendicular to each other, right?
Yeah.
So in circles, you would have heard of the locus called a director circle, right?
Yeah.
Locus of all points which are perpendicular to, from where perpendicular tangents can be drawn to a circle, right?
Yeah.
And that used to be x square plus y square is equal to 2a square, right?
Yeah.
Now here what we are getting is that instead of a director circle, we have a director line sort of, where the directrix basically is the line from where you can find all the points from where perpendicular tangents can be drawn to a parabola, right?
Yeah.
All the points on the directrix you can find, you can draw two perpendiculars which are both tangents to the parabola, right?
Yeah.
That is something that you need to know. Then there are 2 3 more points that sometimes are useful, but what we'll do is we'll stop at this point and you should try some JEE questions, and tomorrow we'll continue from here. We'll finish the theory and do some questions on parabola. Okay,
Okay.
so we'll finish the theory. Theory is almost done. There's nothing much left. This much is enough to actually solve any question. Like you should be able to solve most of the questions from parabola now. We'll try, you should try some JEE questions and we'll also do some problems tomorrow. And that will be parabola. Similarly, we'll take 1 or 2 classes for ellipse and hyperbola also.
Okay.
Okay, that's it for now. I will see you then tomorrow.
Thank you.
Mm.